Okay, today let's try to solve a LeetCode challenge problem. So this is LeetCode September challenge. And today's challenge problem is all elements in two binary search tree. We are given two binary search trees, root 1 and root 2, and we are asked to return a list containing all the integers from both trees sorted in ascending order. So in this example, we are given two binary search tree here, and the output is a sorted array. Okay. And each tree has at most 5,000 nodes, and each node's value is within this range. Okay. One solution gonna be we traverse the binary search tree and store the elements in an array or a list. Okay, in a list. And then we just sort the list, right? This solution won't take advantage of the binary search tree, but it should work. Let's give it a try. Let's define an integer array. And then we need to traverse the binary search tree. Let's do a DFS. And then we need to pass our root and the list. DFS root 2, and then without. Eventually, we need to sort the result list in ascending order. Right? Okay, now let's implement the DFS. So DFS, we need a tree node. Let's call it root, and we also need the result list. If root is null, we just simply return. We don't need to do anything. Otherwise, we keep exploring the left subtree. I'm gonna use the in order traversal here. And DFS. And I'm gonna add my root value to the result. And after that, I'm gonna explore the right subtree. Right. Yeah, it works. Let's try another test case. And the second tree. Yep, looks like it works. Yep, it's accepted, but this one is not an optimal solution. Well, it actually beats 51% of the C# submissions, but this is not an optimal solution. We're not taking advantage of the binary search tree, right? So what is a binary search tree? A binary search tree is a tree data structure that all the nodes on the left subtree has value equal or greater than the root. And also all the nodes on the right subtree has value greater than the root node, right? So the question has passed the daily deadline. Okay, that's fine. So can we use this BFA's property? Yes. What we can do is we can traverse these two BFA's tree together, and every time when we reach a point that is our two pointers points at the minimal element of the binary search tree, we do a comparison between the two minimal value and add the smaller value to our result list. Right, we keep doing that until all the nodes on the two binary search trees are validated. Right, because the current problem, the implementation has time complexity. Let's say we have M node in the first binary search tree, and then we have N node in the second binary search tree. So the time complexity gonna be M plus N log M plus N. Why? Because we need to use the sort function, right? This is dominated by the sort. So if we can use a one-pass traversal, then we can reduce this time complexity to N plus N, right? So let's do that. And if we want to do that, we won't be able to use the recursive way to do the in-order traversal. Instead, we have to do the iterative traversal on the tree, right? Okay, let's do that. We need to define two stacks, and each stack will maintain or store the tree node. Okay, and we have the second stack, which will store all the tree nodes of the second binary search tree. And we can have two pointers. If we don't want to do that, we can use the root 1 and root 2 as our pointers, but let's just use two pointers. Usually I don't like to change the input. Tree node current 1 point to our root 1, and we have the second pointer point 2 our second binary search tree. then we just keep traversing the tree, right? So while if current 1 is not null, or the first stack counter is greater than 0, which means it has some tree nodes. And similarly for the second pointer, we do the same check. This is our second stack. Okay, what we do is we do the in order traversal on the 2 binary search tree. Okay, you count 1, what we do is we push the current to the stack, and then we move the current pointer to its left child node, right? We do the same thing for our second pointer. Okay, so at this point, we're going to compare the top value of the 2 stackers, and the top value going to be the current smallest value of each subtree, right? So we need to handle 2 scenarios. The first one is we need to pop the element from stack number 1, and another scenario is we need to pop the smallest element from stack number 2. So if stack 2 is empty, right? We don't have anything in stack number 2. We have to pop the element from stack number 1. Or if stack 1 has a value and the stack 2 also has value, but stack 1's peak value, the smallest value, is less or equal than the S2 dot peak. What we do is we need to pop the smallest element from stack 1, right? And then we add this value to our result. I don't have a result. Okay, I can add it to my result list. And then I move my pointer to my current root's right child node. Is this right? I pop it from the stack and then I moved it to its right child node, yes. If not, we pop it from our second stack without add right? And eventually we need to return this result. Let's compile the code. "35 and 38, 35 and 38. Oh, yes, since we are storing the tree node in the two stacks, so we need to get its value before we do the comparison. Yeah. "38. So this is the stack 2 has no value, is empty. And the second one is S1 and S2 both have values, yes. Yeah, it works, and let's use another test case. Yeah, accepted. So the time complexity, as I mentioned before, is big O m plus n, right? So it should work faster than the previous one. Yeah, it beats 92% of the C# submissions. Okay, this is today's challenge, and that's it.